We're very happy to have Ljudmila Kamenova for this week's Western Hemisphere Virtual Symplectic Seminar, and she will be speaking on Kobayashi non-hyperbolicity of Calabi-Yau manifolds via mirror symmetry.
Thank you very much for the invitation and for the introduction. This is a joint project with Vafa, which started one time at the Simon Center. Basically, I was having tea there, and Vafa approached me and said, "What are you thinking about mathematically?" So I told him about what math I was doing with Misha Verbitsky and Stephen Lu. And so he said, "Oh, we can do that for Calabi-Yau manifolds." So that's how this project started. And so let me just introduce the main object of this study. Calabi-Yau n-fold. This is a compact, complex, n-dimensional Kähler manifold with trivial canonical bundle and a trivial fundamental group. So here's some properties, general properties of Calabi-Yau n-folds. It has a holomorphic n form that's nowhere vanishing. And also from differential geometric point of view, the holonomy group is contained in SUN. And here's some small examples of Calabi-Yau n-folds. For example, that's one standard example. If you have a non-singular homogeneous degree n+2 polynomial in CP n+1, then the vanishing set is a compact Calabi-Yau n-fold. So, for example, if you have a cubic in CP2, that's an elliptic curve. If you have a quartic in CP3, that's a K3 surface. And if you have a quintic in CP4, that's a quintic Calabi-Yau threefold. So these are some standard examples. And because this study was motivated by the hyperkähler case, I also talk about the hyperkähler case a little bit and see what are the differences. So hyperkähler manifold, this is basically a Calabi-Yau manifold together with the everywhere non-degenerate 2-0 form. So having everywhere non-degenerate 2-0 form implies that the canonical sheaf is trivial, because then when you take a wedge of this form enough times, it gives you a global non-vanishing section of the canonical sheaf. Then from differential geometry point of view, hyperkähler manifolds have holonomy group, which is the compact symplectic group SPN. And by Bogomolov's decomposition theorem, if you have compact Kähler manifold with trivial first-chain class, it decomposes locally as irreducible hyperkählers, Calabi-Yau manifolds, and some tori. But the tori are not simply connected, so if you consider simply connected building blocks of compact Kähler manifolds with trivial chain class, first chain class, then you just get blocks that are either hyperkählers or Calabi-Yau manifolds. So the most simple example in both cases are K3 surfaces. Both hyperkähler manifolds and Calabi-Yau manifolds are higher dimensional analogs of K3 surfaces. And what is a K3 surface? It is a compact, complex surface with trivial canonical sheaf and trivial first Betti number. So here we don't have to assume that the K3 surface is scalar, because by results of many people like Kulikov, Siu, Todorov, we have that every K3 surface is scalar. And also one can prove that from this definition, it follows that every K3 surface is simply connected because first you prove that any two K3 surfaces are deformation equivalent to each other. So in particular, each one of them is deformation equivalent to a quartic in CP3, and that's simply connected because it's a complete intersection. So then another thing what you can do is you can compute the Hodge diamonds and see that H20 is generated by a non-degenerate holomorphic 2-0 form. And the holonomy group of K3 surface is SU2, which corresponds to the Calabi-Yau case. And it's also the compact symplectic group SP1, which corresponds to the hyperkähler case. So because you have these isomorphisms between Lie groups in small dimensions, then both Calabi-Yau manifolds and hyperkählers are generalizations of K3 surfaces, but that's the only case you get in common. After that, they're different. Or you can think of hyperkähler manifolds as specific Calabi-Yau manifolds. So in the Calabi-Yau case, you have a lot of examples. However, in the hyperkähler case, you have very few examples. You have K3 surfaces, then you have some standard examples of Bouville and Fujiki. So, for example, you can take Hilbert schemes of points on a K3 surface, and then you can also take the generalized Cumrun varieties. This is the same as the previous case, but instead of a Hilbert scheme of a K3 surface, you take a Hilbert scheme, let's say, of n+1 points on an abelian surface, and then take the fiber of this natural morphism that maps the Hilbert scheme of n+1 points of A to the sum of the points, which is mapped to A. So the fiber over, let's say, the 0 point is the hyperkähler manifold. And for a while, these were the only examples known in for higher dimensional hyperkähler manifolds. And then O'Grady constructed two exceptional examples in complex dimensions 10 and 6, basically by desingularizing some moduli spaces of semi-stable sheaves. You can think of the Hilbert schemes as moduli spaces of stable sheaves on K3 surfaces and abelian surfaces. But what happens if you take moduli spaces of semi-stable sheaves? You get some singularities, and only in these two cases you can resolve them and get exceptional examples of hyperkählers. So I also want to mention how the SYZ conjecture looks like in the hyperkähler case. So, for example, if you have K3 surface, one standard example of a K3 surface is elliptic K3 surface. And one can study a lot of the properties of K3 surfaces by studying elliptic K3 surfaces. Because for elliptic K3 surfaces, you have Rayleigh in an easier way. They're dense in the moduli space of K3 surfaces. So some of their properties can be used to reduce properties in general. And the same is true in the case of hyperkählers. So if you have any vibration from a hyperkähler manifold to some base positive dimension, then it's very restrictive actually. The dimension of the base is precisely half of the dimension of the total space, and the general fiber is a Lagrangian abelian variety. It's Lagrangian with respect to the holomorphic 2-0 form. And moreover, Huang proved that if the base is smooth, then the base is precisely the complex projective space CPN. And in hyperkähler geometry, people have this conjecture that the base is always smooth, and therefore is always CPN. And this was proved in complex dimension 4. And of course, complex dimension 2, if you have a K3 surface, then the base is always CP1. But if you have a hyperkähler complex 4-fold, then if you have a Lagrangian fibration, then the base is CP2. And there is also the Bouvier-Bogomolov-Fujiki form for a given hyperkähler M. This is a non-degenerate integral quadratic form on the second cohomology of signature 3 B2 minus 3. It satisfies the Fujiki's relation. Basically, if you take 2 class in cohomology, its top self-intersection is some positive constant times a power of this quadratic form. And this generalizes the intersection pairing on K3 surfaces. So Bogomolov first discovered this kind of a relation in his paper from the 70s, when he was trying to prove that there are no hyperkähler manifolds in dimension higher than complex dimension 2. So he thought that the only hyperkähler manifolds are K3 surfaces. And basically his argument was something like, well, they satisfy such a nice relation, so this cannot be possibly true. But this is indeed true. We have higher dimensional hyperkähler examples, and they do satisfy this relation. So here is one trivial observation. If you have a fibration, so given a fibration, let's assume that the base is smooth. And if you take an ample class on the base, then the pullback is net, and it satisfies that the quadratic form Q of alpha is 0. This is because, well, let's go back to the previous slide. Since alpha comes from the base, then alpha to the n plus 1 is 0, so alpha to the 2n is definitely 0. So 0 is equal to some positive constant times Q of alpha to the n. So then Q of alpha should be 0. So this observation is trivial, but then people conjecture that the opposite implication is also true. If you have an F-line bundle on a hyperkähler manifold with vanishing Bouvier-Bogomolov-Fujiki form, then this line bundle induces a Lagrangian fibration. And this is the hyperkähler version of the SYZ conjecture. And while in general this is not known, we know it for all of the examples of hyperkählers we have. So this conjecture is known for the formations of Hilbert schemes, generalized Cumrun, and for Grady's exceptional examples. Okay, are there any questions up to here? So if not, then I'll introduce what are the Kobayashi conjectures and how we will apply them to hyperkähler manifolds.
Can I ask a quick question? Sorry, I just to understand the conjecture you stated here. Is the conjecture that there's a unique Lagrangian fibration in a suitable sense associated to a given L, or just that there exists one?
Just that there exists. There may be many fibrations. In some sense, there will be finitely many fibrations, but it's an existence conjecture.
Thanks.
Oh, would you be able to give a bit more intuition on the Q, what the role of the Q of alpha is?
So the Q basically it generalizes the intersection pairing of a K3 surface, and the way to construct it is you take a class alpha and you start intersecting it with the holomorphic 2-0 form and its conjugate enough times to get actual number. And this is related to the Hodge-Riemann bilinear relations. So you construct something similar to what people are doing with Hodge-Riemann bilinear relations to construct this form. And why you want it is because for K3 surfaces, you have two Rayleigh theorems, which basically classify a K3 surface by its period point, which is you take the moduli space of K3 surfaces, and then you take for each one of them you consider the intersection form on H2, and then you see what is the image of the period map when you apply it to H20. And so basically in hyperkähler geometry, people want to copy this. For a while, two Rayleigh theorems were not known, and people still thought, well, there should exist something like a Rayleigh theorem for higher dimensional hyperkähler manifolds. And so with a lot of effort, people at the end, like Verbitsky established Rayleigh type theorems for hyperkähler manifolds using this intersection, quadratic intersection form on H2.
Thank you.
Okay, I'll talk a little bit about this in a few slides. Okay. Yes. So now let's introduce the Kobayashi pseudometric on M. So this was introduced by Kobayashi almost a century ago, and this is the maximal pseudo distance such that if you have any holomorphic map from the unit disk with a Poincare metric to the given complex manifold M with this pseudo distance, this is distance decreasing. So what is the pseudo distance? This is distance function that measures the actual distance between 2 points on a complex manifold. Why is it a pseudo distance? Because even though it satisfies the triangle inequality, it can happen that the distance between two different points is 0. And that's why it's called a pseudo distance. And a manifold is called Kobayashi hyperbolic if this pseudo distance is an actual metric. So if for any two different points, the distance between them is strictly positive. And Brody proves that if you have a compact complex manifold, then M is Kobayashi non-hyperbolic, if and only if there exists an entire curve on it. An entire curve, this is a non-trivial holomorphic map from C to M. Non-trivial means it doesn't map to one point. So he actually, his theorem in the classical sense, it states that M is Kobayashi hyperbolic if and only if there are no entire curves. But because we'll be proving Kobayashi non-hyperbolicity, here is the negation form of this theorem. And here's some of Kobayashi's conjectures from the 70s. If you have a K3 surface, not only is Kobayashi non-hyperbolic, but the whole pseudometric is identically 0. And the same for hyperkähler manifolds. Here is a slightly weaker version. A hyperkähler manifold is Kobayashi non-hyperbolic, and a Calabi-Yau manifold is also Kobayashi non-hyperbolic. So it took people a while to make progress towards these conjectures. So for example, in the early 80s, Mori and Mukai proved that if you have a projective K3 surface, then it's dominated by families of elliptic curves going in different directions. And the elliptic curves are possibly singular, but that doesn't matter for the Kobayashi conjectures, because what happens is you take two general points on the K3 surface. So then you can take one family of elliptic curves going through one of the points, then take another family of elliptic curves going through the other point, and then along each elliptic curve, the Kobayashi pseudometric is identically 0, and then take the intersection point. So then, using the triangle inequality, you see that the pseudo distance between any two points is 0. So, so at least for projective K3 surface, we have that the Kobayashi pseudo distance is 0. Then, then it took us 20, maybe 30 more years to prove that for hyperkähler manifolds of each known type, each one of them is Kobayashi non-hyperbolic. Basically, with Misha Verbitsky, we were interested in the SYZ conjecture and the density of Lagrangian fibrations. Because for the moduli space of K3 surfaces, if you consider the ones that are elliptic K3 surfaces, they're dense inside of the moduli space. So we thought, well, there should be something like this in the hyperkähler case as well. So we did prove density of Lagrangian fibrations for hyperkähler manifolds. And so what happens is every time you have a Lagrangian fibration, because the general fiber is Lagrangian abelian variety, you have non-hyperbolicity. And there is a theorem of Brody which says that non-hyperbolicity is preserved in the limit. So if you have a family of complex manifolds, which converges to some other complex manifold, then and each one of the members of this sequence is non-hyperbolic, then the limit is also non-hyperbolic. So if you have a density of Lagrangian fibrations, then basically you get any point in this moduli space as the limit of Lagrangian fibrations, which are non-hyperbolic. So every point is non-hyperbolic. So that's the idea. And then it took us a couple more years. Meanwhile, Verbitsky has some results about ergodicity of complex structures on hyperkähler manifolds. And using these ideas, together with Stephen Lu, we proved some stronger results. So if you have a K-tree surface, doesn't matter whether it's projective or not, then the Kobayashi pseudo distance vanishes identically. And then in the hyperkähler case, you have two cases. Either the Picard rank is maximal or not. If it's not maximal, then you have to assume that the given hyperkähler is the formation equivalent to a Lagrangian fibration. Then the pseudo distance vanishes. And if you have a maximal Picard rank, then you have to assume something about the Betti numbers. So if the second Betti number is greater or equal than 0, and the SYZ conjecture holds for all the formations of the given hyperkähler, then the pseudometric vanishes. Notice that this assumption on the Betti number is not so strict because all of the known examples of hyperkählers satisfy this condition. So the smallest Betti number that we know is 7, then 8, and it goes up to 24, 25. For all of the known examples, we do have the SYZ conjecture, and we do have this as a corollary of the SYZ conjecture, that if the SYZ conjecture holds, one can prove as a corollary that any hyperkähler is the formation equivalent to a Lagrangian fibration. So, and people do believe in the SYZ conjecture. So hopefully, eventually one can drop these assumptions. And my theorem with Vafa is that is of more physical nature. Assume that there is a Calabi-Yau manifold whose mirror duo exists, and I will say a few words later what it means not to be Hodge degenerate. Then X is Kobayashi non-hyperbolic.
Can I ask a question?
Yes.
I was curious, going back to the sort of previous discussion about, this Kobayashi non-hyperbolicity, and then there's the stronger statement that the Kobayashi pseudodistance is 0, which is stronger. You mentioned this criterion for Kobayashi non-hyperbolicity in terms of the existence of a holomorphic map from C. Is there a similar criterion for the distance, the pseudodistance being identically 0? Like there's a map to C through every point or something of this form, or I'm just curious.
There is no such condition. There are some implications. So, for example, if you take a non-trivial holomorphic map from C to the manifold such that the image is dense, then you get that the Kobayashi pseudometric is 0.
Ah, okay, with dense, I see. So I see. So if you have a map from C with dense image, then you can deduce it. Okay, that's
but that's very rare.
right. I see.
Yeah.
Thanks. So there's some sufficient condition, but that's in practice pretty rare.
Yes, right.
Okay. Thanks.
Yeah, no problem. So, for example, for K3 surfaces, we know that for any K3 surface, the Kobayashi pseudo distance vanishes, but we don't know. Actually, that's not even true. Not for every K3 surface there exists a dense copy of C inside. So basically, if you have a Cumrun K3, then that's true. You can find a dense copy of C inside. And if you have certain elliptic fibrations, K3s which are elliptic fibrations, for certain ones, there exists such a dense copy of C. But yeah, geometrically, that's how you can think about it. So I promised to say a few words about Torelli theorems for hyperkählers, because that's the reason people were thinking about the Bugil-Bogomolov-Fujiki quadratic form. People were trying to prove Torelli for hyperkählers in terms of Hodge theory. Because for K3 surfaces, this is formulated in terms of Hodge theory. However, there are counterexamples of Torelli using the Hodge theoretic version of Torelli. So finally, Verbitsky came along and he found the correct version of Torelli. So what happens is that for K3 surfaces, if you have the Hodge decomposition on H2, then this is pretty much equivalent to specifying the complex structure on a K3 surface. That in higher dimensional cases, the hyperkählers, these two are different. And so people were really focused on Hodge theory, and that's how they wanted to formulate Torelli for hyperkählers. And Misha Verbitsky discovered, well, since there are all these counterexamples, we should do something different. And instead of doing it with Hodge theory, he did it with a time-Miller space of deformations of complex structures. So Torelli works for hyperkählers, but you have to formulate it the right way. So consider the time-Miller space of complex structures on a hyperkähler. It admits an action of the mapping clouds group, which is the quotient of orientable diffeomorphisms on M modulo some connected component. So for Calabi-Yau manifolds and for hyperkähler manifolds, the time-Miller space is finite dimensional. And let's consider the hyperkähler case, because in the hyperkähler case, we have an understanding of this time-Miller space. For general Calabi-Yau, we just know that it is finite dimensional, but we don't have a complete understanding. So an element, so a complex structure in this moduli space is ergodic if its orbit of the mapping clouds group is dense in the time-Miller space. Okay, and Misha Verbitsky has this more geometric interpretation of what ergodicity means. So basically, for every complex structure, you have this decomposition of H2, let's say with complex coefficients, is H20 plus H11 plus H02. So then you have the two plane generated by sigma and sigma bar, where sigma is the non-degenerate holomorphic 2-0 form associated to this fixed complex structure, and it's a complex conjugate. They span H20 plus H02. So you can think of it as two plane inside of the cohomology H2. So if this, and actually you can define it over the real numbers as well. If you take the direct sum H20 plus H02, you can define it over R. So then, if this two plane contains no rational vectors, then your complex structure is ergodic. So that's how you can think about this in geometric sense. And here is the global Corelli theorem. So in this Ljudmila space that we obtained as the quotient of all complex structures modulo a connected component of the diffeomorphism group, one can identify equivalent complex structures, where equivalent complex structures are ones for which the corresponding hyperkähler manifolds are birational. This gives you an equivalence relation. These birational hyperkählers, they actually correspond to non-separated points in the moduli space of hyperkählers. These are results of Huybrechts. And so this defines equivalence relation. So you take the Ljudmila space, you take the Hausdorff, basically you make it Hausdorff by taking the quotient by this relation, and then you take a connected component. So then Verbitsky's Corelli theorem says that type be 0. So you take the Ljudmila space, mod out by the equivalence relation where two hyperkählers are equivalent if they're birational, take a connected component. So every connected component is isomorphic to this quotient of non-compact D groups. And there is an induced action of the mapping class group which acts on this period domain. And it turns out that this action is ergodic. Ergodic in terms of the Haar measure on the period domain. So basically, Misha Verbitsky discovered not only that you can do Corelli theorems on hyperkähler manifolds, given the correct formulation, but also that there is an ergodic action on the period domain and also on the Ljudmila space on a hyperkähler manifold. So, any questions? So basically, the way we prove these theorems with Misha Verbitsky and Stephen Liu, they're based on the following key proposition. If you have, let's say you're given a complex manifold with some complex structure for which the Kobayashi pseudo distance is 0. And then if you have an ergodic complex structure, which is the formation equivalent to this given one, then even for the ergodic complex structure, the Kobayashi pseudo distance would be 0. And the idea behind this proposition is that the diameter of the Kobayashi pseudometric, this is upper semi-continuous in families. So what happens is if you take the diameter of a compact complex manifold, basically this will be the maximum distance between 2 points on the manifold. It's either continuous in families or it can jump up, upper semi-continuous. So if you have something ergodic, then it means that its orbit is dense in the moduli space. So this given complex structure with zero Kobayashi distance, it's in the limit of some subsequence of these points in the orbit. So then the pseudo distance can only jump up, but it's already zero. And for the ergodic one, the pseudo distance is greater or equal than zero. So since it can only jump up, it must be zero to begin with. So that's the proof of the proposition. It's based on upper semi-continuity. And so basically in the hyperkähler case, since we assume that you have a Lagrangian fibration, then one can also prove that you have density of double Lagrangian fibrations. And so one has to do some work, but it is a little bit like the case of projective K3 surfaces when you have families of elliptic curves, or in our cases, families of abelian varieties going in different directions, covering this hyperkähler. Then you can get 2 points. You can take one family going through one of the points, another family going through the other point, and then see that the pseudo distance is zero. So that's just the basic idea behind these theorems in the hyperkähler case. So that's where the hyperkähler case stops. But unfortunately, for Calabi-Yau manifolds, we don't have such understanding of the moduli space in general, and we don't know if we have ergodicity. So we need different methods. So here is what we do in the Calabi-Yau case. So we introduce, we don't introduce it. This was introduced a long time ago in the physics literature. You have the holomorphic Ray-Singer torsion of a Calabi-Yau n-fold. Basically, this is a smooth function on the Calabi-Yau moduli space. And in the physics literature, it was computed using physics mirror symmetry. And this holomorphic Ray-Singer torsion, or as the physicists call it, the BCOV torsion, or Bershadsky, Chakotay, Ljudmila Vafa. It was computed using physics mirror symmetry, and it was used to predict the number of holomorphically embedded elliptic curves in a given Calabi-Yau manifold. So anyway, there are both physical ways to define it, and now we also have mathematical ways to define this Ray-Singer torsion, also called BCOV torsion. So the mathematical way is using the formula by Feng and Lu. So if you have, so let's take the moduli space of Calabi-Yau n-folds. There is the Weil-Peterson metric on this space, and there's some generalized Hodge metrics as well, which I'll define in a couple of slides. So if you take their Kähler forms, then you can express dd bar of the logarithm of t in terms of their Kähler forms. So this formula has physical origins, but Feng and Lu expressed it in mathematical way. And moreover, for Quintic threefolds in CP4, Feng, Lu, and Yoshikawa computed the BCOV invariant explicitly. So in mathematical way, we have the formula in general for Calabi-Yau manifolds, and we have a lot of computations for Quintic threefolds. So anyway, here I'm not going to talk about the precise definition, but you can see that it can be defined using Chern classes of Hodge bundles. Hodge bundles, which are relative versions of the primitive cohomology groups on a given Calabi-Yau manifold. So you can express both the generalized Hodge bundles and the Weil-Petersson metric. You can express both of their Kähler forms. So this is the formula that Feng and Lu give in their paper. And together with Yoshikawa, they can actually compute things in the dimension 3 case for Quintic Calabi-Yau threefolds. So in the physics literature, basically, you want dd bar of log t to be different than 0 in order to have some non-trivial contributions from curves, like embedded elliptic curves. So then let's express the condition dd bar log t in terms of the Freshen classes of these Hodge bundles. Well, there's the expression. It's a bit cumbersome, but it is a mathematical expression, so one can do this. And we call a Calabi-Yau manifold Hodge degenerate if it satisfies this condition above. So basically, in our theorem, we want the Calabi-Yau manifold to be Hodge non-degenerate. So we want dd bar of log of t to be different than 0. So and that's how we can express it in mathematical terms. And in small dimensions, there's some nice relations between the Kähler forms of the Hodge metric and the Weil-Petersson metric. So for K3 surfaces, that's very simple. In dimension 3, you also have some contribution from the Ricci curvature. And dimension 4, you have something similar. So in particular, if you have a Calabi-Yau threefold, then the Hodge degenerate condition is very easy to express. It just is something like a Kähler-Einstein condition. You have the Ricci curvature of the Weil-Petersson metric is some specific constant times the Kähler form. So that's for Calabi-Yau threefolds. For Calabi-Yau n-folds, it's just a more complicated expression. And I just want to mention in one sentence that Alexis Zinger basically computed the A side of the physical mirror symmetry, which is basically a generating function counting curves or stable nets for Quintic threefolds. And he computed, and together with the computation by Feng, Lu, and Yoshikawa, which was a separate computation on the B side, basically the BCOV torsion side, they separately found that these two expressions agreed. So at least for the Quintic threefold case, all of these expressions agree. And at least we have the physical mirror symmetry for Quintic threefolds. And let me finish by saying that this is our theorem. Assume that if you have Calabi-Yau n-fold whose mirror dual exists and is not Hodge degenerate, so this dB bar of log t is not zero, then X is Kobayashi non-hyperbolic. And when n is equal to 3, this condition of being Hodge non-degenerate is some Kähler-Einstein condition expressed in this way. And I think I'm out of time, so I'll stop here.
Okay, let's thank our speaker.
Thank you.
Any more questions for Ljudmila?
I can make one comment. So, for example, we know that K3 surfaces are Hodge degenerate, but we also know that they're Kobayashi non-hyperbolic. So this condition is not if and only if. If it is sufficient, but it's not necessary.
May I ask a quick question about the last step of your arguments? So is the Gromov-Witten invariant in this case actually enumerative? Is it actually counting the number of, say, holomorphic curves inside your variety?
Yes, so Lagrangian proved that they count stable maps. So let me go a little bit back. So he has this formula. So the Gromov-Witten invariants indeed count stable maps, and you have contribution that comes from elliptic curves, and then here you have some little contribution which comes from rational curves. But like you can take a singular elliptic curve, maybe with a model singularity, then it's a rational curve, like genus zero curve. So much of this understanding of stable maps, it does count elliptic curves.
Thank you. And your Hodge non-degeneracy kind of guarantees the non-vanishing of these Gromov-Witten invariants somehow, and then you're using the earlier sufficient condition for non-hyperbolicity. Is that?
Yes, that's right. Yeah. Yes, so the proof is physical. So basically, if you assume that dD bar of log t is not zero, then the physical mirror symmetry tells you that so on one side you have the BCOV torsion, which from this condition dD bar of log t different than zero gives you that on the A side you have a generating function which is non-trivial. So that's basically where we use mirror symmetry. And this generating function in theory, well, actually that's also using physical mirror symmetry. In theory, it counts elliptic curves. And for the Quintic threefold, this is indeed the case. If you interpret counting elliptic curves in some way of counting stable maps.
Thank you.
Actually, just to make sure I understand that point, is the point that once you sort of know there is an elliptic curve there, you can use some argument around that to deduce non-hyperbolicity? Is that?
Yes, that's
Yes,
the
yes,
Brodik's
yeah.
theorem,
Yeah, yeah,
which is
okay, great,
classical from the 70s. Right.
great, thanks.
So you can have either a smooth elliptic curve, you can even have a singular elliptic curve or a rational curve. This would ensure non-hyperbolicity.
Any other questions? Okay, well, if not, let's thank our speaker again. Thanks very much.
Thank you.